When the geometry or the material behavior get too complex, then analytical methods are not suitable. You need an approximate method to solve the differential equations of your model. That's what we will see in module 26. So we have already seen two modules on joint design, and the method or the approach that we used are simple analytical methods which have a direct mathematical equation to the differential equations that are generated using basic concepts of mechanics of solids. In practice, in many cases, for complex joints or for complex constitutive models of the adhesive or the adherence, the differential equations that are generated become too numerous. There are too many, and there is no direct mathematical solution. In that case, you need an approximate method, and the most common method used is the finite element method. So it's used a lot in the context of adhesive joints. You have here a typical mesh used for single lap joints. I'm sure you have studied already the method, but very basically what we do is that we cut, as you can see here, an element, for example here, we cut the structure in many small elements, and the elements are joined or glued together at nodes. And the objective of the game is to determine the displacement at these nodes. Because once you know the displacement, you know the strain. Once you know the strain, you know the stress. Okay. And one of the methods used to determine the displacement at the nodes is to minimize the energy of the system. And this process of minimization generates a system of equation, which in the matrix form takes this form. Kd equal R. K is the stiffness or the matrix stiffness, which contains basically the mechanical behavior of the element. D is the unknown, that's the displacements at the nodes, and R is the external forces applied. So you solve this, then you know D. Once you know D, you know the strain. Once you know the strain, you know the stress. This is very powerful method, of course. Any geometry, all the stress, not only shear or peel, all the stresses. The problem is that the parametric studies are more difficult. When you want to change the geometry, you need to do a new model. Imagine you want to study the effect of the overlap. You need to generate a new model. So it's more heavy. It's heavier, the analysis. When you use an analytical model, you want to change the overlap, you simply substitute 20 by 30 and that's it. You have an immediate answer. But nowadays, it's probably the most common tool used. One thing you should be careful about is the mesh convergence. You have here stress versus overlap, and the dashed line, this part here is the real stress distribution. So you can see that there is a big stress gradient. If you want to capture this stress gradient, you should use an appropriate mesh, a fine enough mesh. If you use a coarse mesh, then you don't capture properly. You need to refine, especially at the ends of the overlap where you have a big gradient, the mesh. And as you are refining the mesh, then you reach a point where you have convergence and you have exactly the stress that you should be obtained. Then it's not necessary to refine further. But you need to really to do a mesh convergence. But there is a problem, a big problem in the analysis of single lap joints with the finite element method, which is the singularity that exists at the ends of the overlap, these sharp edges here and here. What happens is that at that point, if you refine the mesh, the stress does not converge. It tends to infinity. This is the problem because depending on the mesh size used, you will obtain a different value. How do you solve this problem? Well, you could round a bit. For example, you could average the stress at that point. You could distance yourself from that point. These are all techniques that have been used, but nowadays the approach used to deal with the singularity and deal with other problems actually is to use damage mechanics, and in particular to use cohesive zone models or cohesive zone elements. So for the adhesive you use cohesive element. Very, very powerful method because it combines several approaches. It combines the continuum approach where when you reach a stress limit or a strain limit it fails, and the fracture mechanics approach or the fracture mechanics approach, which assumes that the structure has a crack. Associated to the cohesive element you have a cohesive law, a triangular law. This is the most common type of law, but it doesn't mean that's the only law. You have also trapezoidal laws, which are very common for ductile adhesives. And how does this law relate the stress in the adhesive to the displacement of the two nodes in the adhesive? Well, it starts in this point. You are loading the joint and you are initially in the elastic range. If you unload, you go back to this point, nothing happened to the joint. Now, if you reach this stress, then if you used the continuum mechanics, you would limit, or you reach the limit of stress and it would fail. That's it. But it doesn't fail because you are combining continuum mechanics and fracture mechanics. So from this point, you will have damage of the adhesive. The adhesive will start to damage and will follow this line. If you unload from this point, for example, and you load again, you will see the stiffness degrades a bit. Okay, the adhesive has degraded and the joint, the overall, has lost a bit of stiffness. But let's carry on the load. We are increasing the load, increasing, follow this line. It's degrading more, degrading more, degrading until you reach this point. When you reach this point, the adhesive will disbond because the area is equal to G1C, the fracture energy of the adhesive. And then you will have a disbond here and here at the other ends. And it carries on, and you have the generation of a crack. Initially there is no crack, but once you reach the point where the energy absorbed is equal to the fracture energy, then you will have a disbond, you will have a crack generation. And then it carries on, it goes further until you progressively crack the joint and it finally fails. You see, really powerful. Initially no damage, you reach a failure, a stress limit, it starts to damage, and when you reach the fracture energy, you have a disbond. And this is a progressive process until the joint fails. You have here an example of what you obtain using a DCB specimen, double cantilever beam, fracture mechanics specimen. It's bonded and you load it in mode 1 and it's progressively failing. Using cohesive zone elements, you can very nicely simulate the progressive damage and cracking along the DCB. So really finite element methods, very, very powerful method. And if you combine this with the damage mechanics, you can solve the problem of the singularity and simulate not only initial damage, but the whole cracking process in the joint.
In this demonstration, we use the Single Lab Joint Designer, a modeling tool for Abacus CA. This tool has been developed by Adhesiove's Advanced Joining Processes unit. When we start developing a simulation, there are several steps to take, starting with designing our parts, meshing them, applying boundary conditions, and so on. This tool will allow us to do all of that, but in a much simpler way, using these input windows. Initially, we must define the dimensions of our joint we want to simulate. For this, we need to consider both the substrate and the adhesive dimensions. Then, in terms of materials, we can choose both the substrates and the adhesive materials using this window. We can perform an analysis of dissimilar or similar joints by selecting the adequate materials. For each substrate we can define its behavior as elastic or plastic, and the same is applied for the adhesive. In this case, we will use squeeze zone modeling, which defines squeeze elements along the overlap length, which will allow us to capture the failure load and mechanism. In terms of mesh, we will divide our dominium into small subdivisions having larger and smaller elements, according to what is needed. This will be detailed later. Finally, the last step is applying boundary conditions and defining some simulation details. For this example, a displacement of 1.5 mm is applied to the end of our joint, while the other side is fixed. We can define our job or simulation name and the amount of CPUs that we want to use. Now we can generate our model and submit the simulation. While we wait for the simulation to be finished, we can explore the meshing environment in Abacus, and for that we can go to the mesh module. Adhesive joints usually prefer a finer mesh near the adhesive, especially near the stress concentration points, in order to better capture the stress field and failure mechanisms. However, the rest of the model doesn't require such finer meshes, hence a coarser mesh is used in non-critical areas in order to save computational time. With this explained, now we can go back to the single lap joint designer module and visualize the results since our simulation is now finished. Here we can analyze several parameters such as the von Mises stress and use animations to see our joint failing over time. Another parameter that we can analyze is the S-tag, which defines the damage accumulation on the adhesive layer from 0 to 1. We can see through a graded scale that as the joint is being tested, the damage in red is being accumulated while the joint fails progressively. And with that we concluded the tutorial.